So welcome to part 2 of finding derivatives and integrals. So in the last video we left off on the chain rule, and now we're going to do some problems. And I think the chain rule is very complicated to get, so we're going to do around 2 to 3 problems here. So let's say we have this function y equals 2x minus 5 to the 7th power. Now you can't distribute, you can distribute this function actually, but it's going to take lots of effort. But what you can use is the chain rule. The chain rule can help us find derivatives of functions like this, because you have a function inside of a function. So we write the derivative of y as y prime, and that will be equivalent to, we got the outer derivative, so outer will be 7 times 2x minus 5, and then we subtract the exponent by 1 if we use the power rule, times the derivative of the inside. In this case, it's going to be times 2, and that will be that can be simplified into 14 times 2x minus 5 to the 6th power. Now let's go ahead and do another problem here. So we got y equals basically, let's go ahead, y equals 6x times x plus 7 to the 6th. Let's do 7x plus 7 actually. So what we gotta remember is that we have multiple rules in use here. We have the product rule, power rule, and the chain rule basically. So we're going to find we're going to use the product rule. So f of x times the derivative of the g of x. So that's where we're using the chain rule here. So we do the outer derivative. So that's 6 times 7x plus 7 to the 5th power times the inside derivative is 7 plus 7x plus 7 to the 6th power times 6 basically. And of course, we can go ahead and simplify this. First of all, just multiply the 6, and 7. So that's actually 36 times 7. Since I don't have a calculator, I can just go ahead and ask my Alexa, what is 36? Alexa, what is 36 times 7?
36 times 7 is 252.
Anyway, that's 252 times 7x plus 7 to the 5th. Plus, we got 6 times 7x plus 7 to the 6th. Now you can simplify further, but let's go. We're gonna go ahead and find derivatives of exponential expressions next. So how do we find derivative of exponential expressions? So let's go ahead and know what an exponential expression is. So we were used to finding expressions we can use the power rule with expressions with a variable in the base and an exponent as a value. And in this case, we're going to find the derivative of functions where we have the base as a constant and the exponent as a variable. Now, this is This is a very complicated pattern, but it's not complicated. So if we use the chain rule here, we can go ahead and can use the chain rule here, and then this is n to the power of x times ln of n. And I put parentheses in order to avoid confusion. So let's go ahead and try this. Let's try a few problems here. So let's try one problem, y equals e to the x. And what about y prime? Y prime will be equivalent to, we got n to the x, so n is going to be e in this case. E is a constant here, Euler's number. E to the x times ln of e. And since the natural log of e is 1, this will simply be e to the x. And coincidentally, this function is the same as its derivative. The derivative of e to the x will be e to the x. So now let's do another problem here. So let's do y equals, this time, we got 5 to the power of 3x minus 6. How will we find the derivative now? So since we have a function in the exponent, we have to use the chain rule here. So we can still follow along with the pattern, exponential formula pattern. So we got 5 times 3x minus 6 times ln 5. That's the derivative of that's going to be the outside derivative. Now the inside derivative is going to be 3. However, we can't multiply the 5 and 3 because they have different exponents. So this will be our final answer. 5 to the power of 3x minus 6 times ln 5 times 3. And this is how we use exponential functions here. Now we're going to talk about implicit differentiation here. So we know how to differentiate with respect to one variable. And differentiate is another way of saying finding the derivative. So, on the other hand, we need to find derivative of the expressions with two variables here. I know this is not multi-variable calculus, so but basically what you can do here is find the derivative of this function here. So we want to find the derivative of x squared plus y squared equals 25. So this is going to be very different because what you want to do here is differentiate both sides with respect to x. So we're getting used to a new notation called Leibniz notation. D over dx is also how we find the derivative here. And then we want to go ahead and do d dx on both sides, because whatever we do on one side, we have to do to the other side as well. And simply, we want to take the derivative of all the terms here. So we got 2x plus. Now we are going to find 2y here. We're going to find the derivative of y squared. That's going to be 2y, but we're differentiating with respect to x. So we're going to add a dy dx. And this is very useful whenever you do word problems relating to derivatives, like for example related rates. And for example, now we got 0 as 25's derivative. So now what we want to do is solve for dy dx. So now what we want to do is subtract 2x on both sides. So negative 2x equals 2y dy dx. I swapped the two colors, but yeah, I don't care. And then we want to divide 2y on both sides. So that leaves dy dx to be negative x divided by a y. However, we can also rewrite the derivative in terms of x. So now what we want to do is solve for y here. And we know how to do this. This will be the square root of 25 minus x squared. So this will be the same as negative x divided by the square root of 25 minus x squared. And this is how we do implicit differentiation. Now let's go ahead and work with inverse functions and inverse trig functions. So now we're going to go ahead and find let's go ahead and try to see if we have the function here. So we got, let's say g of x equals g of x will be equivalent to, we got 3x squared minus, actually, let's go ahead and work backwards, plus 5 plus 8x. And let's say you want to find the inverse function here. It's not possible to find the inverse function here since we have a polynomial quadratic in the form ax squared plus bx plus c. But what we can do is find the inverse derivative at a value here. So we want to find the inverse derivative at, let's just say, 2 here. So how do we find that? So that's going to be equivalent to 1 divided by the g inverse prime. Actually, the g inverse prime of 2, I mean. So that's going to be the g prime of the inverse of 2. Let's consider doing negative. Let's actually do 5 here. Ooh, gosh. So that's g prime of the g inverse of 5 here. So now what we want to do is set the inverse here. So 5 is that we know what the inverse is. X and y swap. So we can plug in x5 for the g of x. And that will be 3x squared plus 8x plus 5. And the 5's cancel out, and that leaves 0 equals 3x squared plus 8x. And we can factor this, factor an x out of it, x, and then we got 3x plus 8. And if you notice that x is equivalent to 0, and x is equal to 0, and of course you got x equals negative 8/3. So notice how the inverse isn't exactly a 1-to-1, but we found the values here. So we can go ahead and find the inverse of each. So we can now find the derivative of the inverse function of the g of x. But we're running out of time, so we'll continue in another video.